Hey, so this is a video on Andre Karpathy's Micrograd, which I re-implemented in Go, and I'm going to go through um, the Python implementation and the Go implementation side by side. So obviously I did his video, which is excellent, building Micrograd from scratch, and then I also on top of that implemented the Micrograd demo, which is a bit more complicated than the examples he gives in the video, and a bit more interesting as well, I think. So let's get into it. So first things first, like if you look at his repository setup, you can see there's no dependencies file in here, which is optional. Actually, hold on, setup. Let's go and look. Okay, no, it doesn't have any dependencies, I don't think. So yeah, I mean in Python you have like one of the great problems with Python is that you have all of these different options for specifying dependencies and whatnot. Um, he just hasn't specified anything, so you kind of just expected to have whatever dependencies your project needs just in the environment somewhere. However, in Go, I have of course got a Go mod file which specifies the version of Go it runs on, um, and the direct dependencies and indirect dependencies, which is great. And then there's the Go sum file, which locks those to a particular version. Okay, so definite win for Go there. Again, if you're familiar with Python, you'll know that it's just a mess. Like packaging Python, just awful. Okay, so let's move on now to like the actual important stuff, I guess, from most people's point of view, which is the implementation. So I guess like the layout of the Micrograd project is different from what was in the video, which is what I'm following. In the video, he just sort of does it all in one Jupyter notebook. Which again, I'm also not using Jupyter. I mean, you can use Jupyter with Go. I just like to use NeoVim to write code, so I didn't try getting Jupyter to work. But anyway, yeah, he just did the whole project in one Jupyter notebook, whereas the actual Microgrid project it's separated out into different files. But I've kind of ended up with two files that are kind of similar in Go to the ones in Python. He's got engine, and I've got grad, which are pretty much the same thing, and he's got nn, and I've got neuron, which again, like pretty much the same thing. And the sort of the module layout between Go and Python is also quite similar. Again, in Python, I think it's purely by convention, whereas in Go, we're forced to write package and everything. So in Go, you know exactly the way you need to do something. In Python, I'm not really sure like what constraints there are and what you can and can't do. For some reason, we have this empty init file, haha, which I guess defines the module. Then we can just have whatever files we want here. And if we go into this file, okay, so in the Go file, we know that we're in the grad package because we have to write it just there at the top of each file. In Python, yeah, you don't have to write that, which is like a continuing theme you'll find throughout this, which is Go very much, you have to be quite verbose compared to Python. I mean, Go is definitely not the most verbose language in the world. I mean, Rust certainly can be a bit more verbose. Okay, so Python, we've got a class, the value class. Go, we don't have classes. In Go, we just have structs, which, you know, fulfill sort of the same niche as classes do, but we can't do things like inheritance with structs in Go. But we can define methods on structs. So yeah, I've got the with prev for with previous method on the context struct, which is just here. Okay, so we've got the value class here. Let's go and find the equivalent of the value class. Okay, it's just here. Right, so you can see that my value class is a bit more complicated than what is in the Python. And part of this is me and part of this is the language. So it may not be, this may not be the absolute simplest, it's definitely not the most simple thing you could do. The ID field could probably go if we wanted it to for a start. And also something else, I guess, what's initialized in the Python class may not be the entire number of fields. In Python, you can just add fields when you want. So I guess there should actually be somewhere around here, there might actually be a label field somewhere. Somewhere in here there might be a label field which is added sort of after the fact. Although you can see here that Karpathy's like deliberately set self backward to lambda none, which is the sensible thing to do, so that people know what's inside your class, but I don't think that's necessary in Python. You can just add and remove stuff as you want. In Go, we pretty much have to specify what we want at the beginning. Another thing you'll notice here is I added a type constraint or a type parameter to my value struct because I wanted to be able to specify either float 32 or float 64 or even float 16, although I don't think Go actually supports float 16, but I can at least switch between float 32 and float 16 using this type parameter. And the type parameter is filled in at compile time, so you have to specify at compile time what type you want, and then you can use either type. Of course, Python has no concept of compile time, or at least not in the same sense as Go. If Python compiles, it usually happens kind of on the fly, whereas in Go there's like a clear compilation step. So this type parameter is actually something we could get rid of and simplify. So wherever you see this type parameter and t, we could actually just replace that with float 64. I mean, in the end, I did a few experiments with float 32, but basically I end up using float 64 almost everywhere. It's just easier. But yeah, definitely in theory you can sort of put a type in there. I'm not sure how useful that really is, but for this kind of thing, especially if you're actually compiling it down to something that will run on the GPU, but it's something you can do in Go. And I think actually you might be able to do something similar in Python as well, but it's not going to have the same performance as in Go. Okay, so in the Python we've got data here, which is of course type T, and of course the init is actually our new function. So if we scroll down here, at some point we should find, okay. So this is the equivalent of the init function in Python. So first of all, we'll go from the top. First of all, like the val function we have here is actually a method that we call on context. And the reason why I have this context object is, first of all, okay, we're storing like an atomic value in here, which is the maximum ID of our value, and I've also got a cached value in here, which we'll get to later. But actually, the reason why I added this type in the first place was, again, because of this parameter, this type parameter just here. I found that, for example, some of the methods to create some of these options just here, like the with label option, if we don't have like a context object with the type parameter on it, then every time we call with label, we have to specify the type parameter of the value args struct, which we'll also come to in a minute. Which got very, very verbose and is really annoying when sort of with label doesn't even need. We don't really care like what the value of t is when we're adding a label, but the compiler demands that we specify what that type is for the value args, even though it really doesn't affect it. Like the label field is string and it's always string, and it doesn't matter which flavor of context object you want, like you still have to like specify it. But if we have this context type, then we can sidestep that problem. But on the other hand, like if we're comparing it to Python, we can see things have got very verbose compared to Python. And of course, in Python, it's dynamically typed, so you can, if you want to switch between float 32 and float 64, assuming you can even do that in Python, you don't need these type parameters. Okay, so yeah, the val creates our new value object, and if we look, so we've got the data argument just there, which I've just called D, being lazy, but it is the data argument. And then we've got this with args varadic argument, which basically captures all of the trailing arguments at the end and puts them into an array, which is an array of value arg. And value arg, as we saw earlier, it's actually a function. So basically, when we create a value, we pass a list of functions to the end of it, and this list of functions, like with grad, then return another function, or rather we use with grad to return a function that goes to this trailing argument with args at the end of val. And if you find that confusing, then you're not alone. But basically, this is a kind of hack, because in Go we don't have this feature here. You don't have named arguments. We don't have named optional arguments in Go. So instead what we can do is we can do this trick, playing with functions that basically we get this list of functions, and then we call each function on a value args structure, and the function can update this value arg structure. I mean, or we could pass value directly, but I chose to create a separate structure, just in case I had to do that anyway at some later time. So basically, yeah, we have to kind of create our own our own named arguments in Go, which is a very, very common pattern in Go. So you'll see this a lot if you're not familiar with Go. And if we go to val and look up some usages of it, yeah, you can see just here, look, we pass like the with label optional argument for that value. So you can kind of see how that works. And of course, sort of the advantage of this, of doing this, is that we have quite a bit of freedom in how we define, like with param. Like I said, you could call it, instead of updating a value args, we could update value or do something else. But yeah, it's very, very verbose compared to Python, where you just write this. Like, we don't have to write with children, blah blah blah. Or actually, I've got with prev here, because again, I think there's a difference between this and the video. But yeah, instead of creating this function and creating this value arg struct, blah blah blah, we could just have a named argument. I'm not sure what Go's reasons for not including this particular feature are. I know that Go is supposed to be like a very what's the right word? Like very sparse or very minimal language. But I mean, this particular feature would actually be quite nice in the full language, seeing as this is such a common idiom in Go, and people often do it in different ways. So you see, like with whatever, and then you go into it and find out it doesn't return a function, or it does something slightly weird, or like, so when you see this, you're never really quite clear on what the actual semantics will be, whereas this you always know because it's part of the language. So I think, while it is, I definitely, one of the reasons I like Go is because it's so minimal, but this is actually one thing where I think, okay, maybe maybe that could actually just be put into the language without many problems. But then I haven't been to look and see what arguments there are around that. Okay. I guess yes, that's how we create val. That's how we do it in Python. Next thing. So got some stuff here. Let's skip down to sum. Okay, that's a different thing. Hold on. Add. Yes. Okay. So next thing, in Python we have this add method, which is actually operator overloading. So in Python you can override the operators like plus, minus, like plus. We've got multiplication. In Python we can override those, the same as in C++, so that we can change the meaning of this symbol when applied to this class. Thankfully in Go we can't do this. I say thankfully because, well, while operator overloading is a great feature for like producing very concise code, when you're writing system code, which is something that Go's used for, you really want to know what is a function call, what is a method call, and what is a simple operator which will be compiled, which will be handled by the compiler. So in Go, you always know when you see the plus symbol, you know that the plus symbol can only be applied to certain built-in types, and it's handled by the compiler. It's a built-in. You can't override it or do anything else with it. Although from the point of view of Micrograd, this isn't so great, because if we go and look at some code that does, yeah, if we look at some code like this, we've got So this is calculating the loss or the losses, the max margin loss. And if we go to my version of this, where have I got that? It's in main. It's the more complicated one. Okay, so yeah. So we can see that, so in Python you can see that he's just put 1 plus minus y1 score 1. And first of all, I've had to define 1 as a value, and then subtract from that expected I, then multiply that by yi, followed by the Relu. So the Relu is the same because that can't be, there's no such operator in any programming language, I imagine. But you can see in Python that this is a very concise, familiar algebraic looking expression. Whereas in Go, we've got a bunch of method calls over one another. Plus, I can't see that this number 1 is an integer, or it's a number value, whereas yi here, I think, or at least score I, will be a value type, an object. So in the Python, if we go to add, at the top here it says if other is equal to other if is instance other value, so it's an instance of this class, else we wrap other in the value. So you can add like any number type to this object, and it'll automatically wrap it in a value. I have to wrap it myself, or else I'd have to add some. I guess I could do it in Go, but if I did it in Go, what I'd have to do is. Oh, actually, no, I couldn't because I'm calling a method on 1. So, I mean, if I was doing it the other way around, what I could do is instead of O being value type, I could set O to the any type, and then I could do a switch statement on the value of O's type, and depending on the type, I could do the same thing that's happening here and wrap it or not wrap it. Which would be worse for performance, but it's possible to do it in Go. Yeah, so I mean it's possible. I mean what I could probably do is add another method that does that. So I could add like another method for every method. Say sub a for sub any, and do like any, etc. Ignore the with args, and then have like a switch, and then there's like some funky syntax like this or something. Am I right about that? In case, I know value, yeah, but we always need to specify the generic type, which is ultra annoying. Yeah, so I mean, or whatever. Like at this point, we could do whatever, or we could, or if it's like a float 64, or maybe can we write t? Can we just say it's case t? Then say val is equal to it'll be v context val o. Cannot use o as index. So I'm not. Go on. Oh no, hold on. I have to. Is that what I have to do? Okay. As you can see, I've never actually really used that before, so V isn't. Oh, come on. No, I've. Okay, but you get the idea. Basically, yeah, I can do a switch statement on that, and we could basically do something similar, which of course would be a little bit slower, um, and add some more code, but we could do that. I just chose not to. Um, okay, so yeah, so you get the picture. Like, for like the really basic operations, we in Python we can override them, including pow. In fact, I just have to point out that I don't know if Go even has pow to the power of, but yeah. But in Go we can't, add these operators. But then the thing is, there's things like Relu, which is a type of activation function, um, which is not in the video, but is what's used by default in the project, in the source code. In the video, he uses tanh as the activation function, whatever. I've implemented both of them. Okay, so when you sort of run out of operators to use, you end up having to do these method calls anyway. So the Go's more consistent there. Yeah, and then blah 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 blah. Ah yes. At the bottom here, you can see this representation built-in function, which controls how the object will be formatted if you print it in a string. And in fact, Go has almost the same thing, which is just oops, instead of being called something weird like representation, instead it's just called string. And basically, when printf uses the v notation, that's when this will be used. So it's actually, yeah, like very similar to Python. Although this in Python, the repro will also be used in the redeval print loop in the repel and stuff like that, I guess. So it's maybe not quite as powerful as Python's, but it's still there in some capacity. Which actually I found a little bit surprising, that Go has that when it chooses not to implement some things, but has stuff like that. But it is really useful, so another way is I understand why it's there. Okay. So go back up to the where is it? The implement the value struct. You can see in Karpathy's version he has this self backwards function, which takes a lambda, or just an anonymous function, or just any function. And I don't have that. Instead, I have op. And see, what backward is used for is when we do the backward propagation, which is when we update the gradients from back to front, which I won't try to explain. Go and watch the original video. Like basically each operation has a different function to calculate the gradient. And what Karpathy does is, in fact, I think what PyTorch does as well, actually, is you have this this anonymous function that's put in there. But I didn't do that. Instead I went for a different tactic, which is I just store the type of operation in the structure. And then when we do the backward pass, we just switch on the operation and do the calculation. So instead of having the operation specified here in each operation, we just have this case statement which is used during backward propagation. We go to backward here, we see that it'll just call, hold on, yeah, it will just call the backward field. There's in Go we could do the same. Go supports anonymous functions or lambda functions. I mean, we saw this earlier with the with these. We can see that these return an anonymous function that we then call to set the options. I did it this way, not for any particular reason. In theory, this could be faster because if it's the case that if the lambda function is compiled to a function pointer that's accessed at runtime. So in some cases, when you use a lambda, it's not going to use a function pointer that's kind of dynamic and can change at runtime. The compiler may be able to figure out that the lambda function will actually always be the same function. So it can even optimize out the function call and stuff like that. But if the compiler can't do that, then you could end up with a function pointer, and sometimes, not always, but sometimes calling a function pointer can be slower. The CPU can find it harder to predict what instructions to load next and stuff like this. It can affect the cache lines and blah blah blah. I mean, it's not always slower. Performance is hard and complicated, but sometimes it can be. Sometimes it can be faster as well. But yeah, I just decided to do it this just to break from what Karpathy did. Of course, you can do this in Python as well. You can do it either way. I guess from a code point of view, it kind of means that I've moved the gradient code out of the code which does the forward pass and sets up the graph, which you can view as a bad thing. But to me, it really doesn't make that much difference. In fact, I quite like all of these being in roughly the same place. But yeah, there's really like no difference there between Python and Go. You can do that in either one. I just decided to be different. Okay. So now let's go and look at main. So in fact, let's go and look at demo, which for some reason has disappeared. What's going on there? Doesn't seem to like that. Okay. So now I'm afraid that Go really doesn't perform well once we get to this. Okay, so again, if you've done the video but you've not actually looked at the full Micrograd, there's quite a more complex, a bit more complex example in the full Micrograd, which takes some sample data and then fits to it. So you can train a neural net that predicts whether a sample point will be in the red area or the blue area, which has been created by this moon data set. And okay, so if we could do a comparison of the Python and the Go in this particular case. Okay, so there's some differences in the code structure here which are just arbitrary, but I mean, okay, so first of all, he uses this data set from sklearn. I had to recreate this data set. It's actually just a data set that's generated on the fly. I actually just was really lazy and just used GitHub Copilot to generate this. I was looking at the sklearn source code, trying to figure out how this make moons function works, and I didn't understand the Python. But apparently, you know, GPT has no problem converting this to Go. So yeah, you can see that if I go here and go to, where is it, moons? Yeah. So yeah, so the Go version generated this, which is quite similar to the Python one. And also in the Python one, he uses matplotlib to plot this, which is quite like a simple plot. Okay, it's a bit more complicated in the Go, and this is, I guess the point here is this isn't really saying anything about Go the language or anything. This is actually saying something about the ecosystem. So Go has these libraries that help with this stuff. You know, it has GoNum, which comes with a plotter. What's it called? Yeah, GoNum plotter. It has this stuff, but it's not. It doesn't have the same depth as the Python libraries. So it's a bit more verbose to generate the plot. And also, there's the plot at the bottom here where it shows the heat map or whatever. I tried to convert this using GPT and it just wouldn't do it. I mean, again, there's stuff in the GoPlot library that should be able to do it, but it just got horribly confused and wouldn't do it. And I wasn't too interested in actually getting that to work. But basically, you know, especially in the case of this one, I think regardless of what you do, this is going to end up being quite verbose in Go compared to the Python. So yeah, anyway, moving on to like the actual neural network. So, okay, so let's see, where do we start? So this is the loss function just here. And here we have the optimization function, which includes the loss function. I didn't separate it out into a loss function and an optimization function. I put them all in one function because here he's doing it in basically because he's doing it in Jupyter and he has global variables all over the place. This function actually accesses global variables that then, if I want to, like, either I'd have to make those real global variables in Go, or just, you know, I can just, or have like loads of arguments to this function, and I got fed up with how many arguments I had, so I decided to just put it all in the same function. It makes very little difference anyway, having an extra loss function to me. But this does complicate it a bit, sort of looking at where the loss function begins. But if we zoom in on this, so inputs. So we've got inputs here. Set activation. Okay, so first thing is, okay, so this extra bit of code here, I'm updating the activation functions from tanh to Relu. Because in my library it defaults to tanh, which is the same as the video, but in the repository he's using Relu only. But so I decided to keep both, and I update this to use Relu just here. So I've got the inputs, which he calls the inputs x. Where's x defined? I think it comes from the moon data set. So it's x and y. I find this kind of confusing. Y is actually it's not the y coordinate, it's the class that each data point belongs to. And x is the coordinates of where each data point is, the coordinates of each point. So I found this a little bit confusing at first, but I guess this is in line with some machine learning theory, I guess. So y starts off as a 1 or a 0, and then you have to change it to -1 or a 1, which just tells you whether it's in the red or the blue class of points. So okay, so I've called that inputs, and so I have to okay, so yeah, he's also called it inputs. Basically, for some reason he creates the inputs every time inside the loss function, whereas I do it outside of the loss function at the beginning once, which is like a minor optimization. But the important thing, as you can see here, he's using a list comprehension and the map. He's using the map function and the list comprehension. In Go, we definitely don't have list comprehensions. Yeah, I think there's a map function somewhere. Somewhere in the Go library there's a map function, but I couldn't find it, or I couldn't remember where it is or how it works. So instead I just used a for loop. And actually just here I would have to have two for loops, but I added a utility function which takes a list of type T or type float, whatever, and then turns them all into values. Because there's a number of places where we basically end up with two nested for loops in order to turn a bunch of inputs from an array. Yeah, you can kind of see it here. You end up with like this nested for loop just to map all of these input values to the value object, which is like really verbose and annoying. And of course, with list comprehensions, you don't have to do that, and it's much more concise. I mean, list comprehensions I do find more difficult to understand, but only slightly. I use them a lot in Julia, so I kind of get them, but yeah. So I mean, the Go is much more verbose. The map function, map that takes a function and then applies it to everything in the list. I'm sure this. I mean, I can certainly write a map function in Go that does exactly that. It must be inside the Go library somewhere. But like the idiomatic way in Go is actually just to make a for loop. Okay. Actually, I guess one thing as well is that the for loop, when you're writing a for loop, you can clearly see that like we're updating the array and we're updating it with a new value. When you use a map function like this, it's not always clear, like, does the map function return a new list? Does it update the array in place? Does it return an iterator, which is why we then have this list function wrapping it to turn it into an actual list rather than just having an iterator object? It's not instantly obvious from looking at it. I guess that, if you know Python, then of course, yeah, you can probably tell what that does. But in Go, like, you really can't mistake that this is updating this array in place, and we know that we're making an array. Okay, but yeah, it is a lot more verbose. And then for calculating the scores and losses, when you look at something like this, I mean, you can tell that obviously, like, this expression here returns an object because then we're calling dot Relu on it. But, I mean, you could certainly ask, like, well, what object? Like, what type is that returning? You know, would this code make any sense if you didn't have contextual information? Like, we didn't know that score was a value object, and that when we multiply a value or add a value object to a normal number, that number then gets subsumed into a new value object and it all turns to the value type. You can kind of guess something like that from the fact that they're then doing a method call on it, but there's a lot of like magic going on underneath the surface here that in Go, okay, like it's nowhere near as concise. Like we've got like, how many lines have we got? We've got like 2 lines in Python. We've got like 1, 2, 3, 4, 5 lines in Go. I mean, you could maybe, yeah, I mean, you could have like very long lines, I suppose, but yeah, it's a lot more verbose. But you can tell, like, we know straight away, like what type this symbol is, and that we're doing a method call on it, and blah blah blah. You know, and expected is an array, and all of this. But yeah, I mean, it's a lot more. And I mean, actually, something nice in Python we see here is zip, and then using zip to have like to go through 2 different arrays in parallel. Although, I mean, in Go, it doesn't actually end up being a lot more verbose because we can, you know, iterate over scores while getting the value from scores and the index from scores. So then we can use the index from scores to iterate over losses as well. So, I mean, the actual value we get from having something like zip isn't huge compared to this. Okay, and then we got LT regularization. Again, it's actually like a lot more lines to calculate this than in Python. One of the lines is hidden up here actually, so we've got 1, 2, 3, 4, 5, 6, 7, 7 lines versus 3 in Python. Yeah, just same thing over and over again. It's gets a lot more verbose. Okay, and let's just go and run this. So because I'm not using a Python notebook, I just have a main function that I run as well as tests. As you can see, like the output is somewhat similar in mine versus it. There's actually an interesting difference in the loss. I find that my loss gets down to about 0.03, whereas his goes down to 0.01. And yeah, it struggles to get below this point. So there's maybe there might be something wrong with my calculations, but as you can see, it still manages to get up to like 100% accuracy most of the time. But yeah, there's just some reason it does take a bit longer to get there. And the performance is also, you know, it seems exceptionally bad. And why, I don't know. And it's not of huge interest to me, like how fast this is, because I mean, realistically, I mean, I could try optimizing it, but ultimately you really want to be running these kind of calculations on a GPU, or if not on a GPU, you still want to be doing it on the CPU in like a highly multi-threaded way, and there's just like a whole load of work You want multiple threads, you want to have vector instructions, like there's loads of stuff you want to do, and like optimizing it a little bit just doesn't seem worth the effort to me. I mean, I'm sure that I could get pure Go to be much, much faster than pure Python, but still, it's like really what we want to be comparing is like OpenCL kernels or CUDA kernels, in which case the language that you're, constructing your graph in doesn't matter too much. So, what else have we got? I think that's it basically. I've also got a test suite here as well, which, yeah, so I've got a bunch of tests that I did, which I did that to begin with. I did quite a lot of testing and then stopped. And as you can see, there's a problem here. Apparently, I must have changed something for the worse to be sure. Anyway, yeah, that's it. I hope you enjoyed my video rambling about the differences between Python and Go.